Welcome to this video. We continue discussing machine learning, and in this lecture, we're going to talk more about machine learning concepts. We're going to discuss the package that we're going to use in Python to create and evaluate these models called scikit-learn, and then we're going to introduce one machine learning model called linear regression. Let's first talk about scikit-learn. There are many machine learning libraries in Python, and scikit-learn is one package that contains a large number of models, and it has a consistent and very easy to use API. We're going to use scikit-learn in this course. First, I'm going to load one data file called iris. This is one of the classic datasets used to evaluate machine learning models and specifically classifiers. In this package, in this dataset, we have 5 variables: sepal length, sepal width, petal length, and petal width, as well as species. So those are measurements to different flowers of different species, and species is basically what we want to predict using these measurements. Now, in the lingo of machine learning, these variables are called features. So features are the variables that we are going to use in order to predict the outcome. And when we have a data set such as this one, it has a size, a shape, which is the number of samples, the number of observations, times the number of features. This matrix is specifically called the feature matrix, or many often we use the variable name x, because we can think about creating a machine learning model as estimating an outcome, which is y, based on an input, which is x. Now, this is x in capital letter because we have a matrix, we have multiple of these features. Each one of these features is a small x dimension, x1, x2 to x number of features. On the other hand, the variables that we want to predict is called the target array. And we usually use the symbol y with a small y because many often we have only one thing that we want to predict. Now, this is not limiting because even if we have two things that we want to predict, we can think about them as tuples in this array. So we can still use y in a small case kind of to indicate that we have a vector of values that we want to predict. Now, in supervised machine learning, we usually want to predict y given x. And depending on what y is, we have either classification or a regression problem. If y is a categorical variable, such as in this case, for instance, species names are a bunch of categories: Setosa, versicolor, let's take a look here, and Virginica. This is an example of a classification. If the y target array is a continuous variable, we have a regression problem. Many often we start looking at our data before applying a machine learning model to it. And the purpose of this exploratory analysis is to gain some understanding of what we have before trying to use a sophisticated model. Once again, visualization is a very powerful tool that we can employ here. This particular kind of a graph is called a scatter matrix, and it's basically a combination, it's a bunch of scatter plots for each two of these variables. And I have colored the circles here using the target variable, the target array y, which is the species. That basically gives us some, understanding of, how these different variables, the features, relate to the outcome variable. Like, for instance, if you take a look at this scatter plot, you can see that, well, if you look at petal widths, it's definitely discriminating against the species, the target array. So discrimination in this case is a good characteristic of the variable because it allows us to separate observations of the first category from observation of the second category. We can also see that, well, although its petal width has a very discrimination power in between Setosa and versicolor, it's not that the case for versicolor and Virginica because there is some overlap. And one can take a look at the remaining variables, and if you take a look at many of them here, you can see that some of them, such as sepal width, are not very useful. Sepal length is not very useful either. And we can also see that it's much more easier to separate the blue dots the from the rest compared to separating the orange and the red dots from the rest. The fact that we cannot separate all of these dots from each other when we have a machine learning model doing the classification is called confusion. And there are some measurements that we will look at to detect them, to evaluate the model accuracy that relies on how the model is confused when it tries to classify the observations. So this kind of analysis is important before trying to model the data using any machine learning model. What I am doing here, I'm separating the X from the Y. So basically I'm taking only, I'm dropping the species from the data frame, and I'm left with a data frame containing the remaining 4 features. That's my feature matrix. The Y, the target array, is basically the target variable, which is species. And that's basically the shape of the matrix and the target variable here. When we use scikit-learn, the process of creating a model and evaluate it is similar across different classes of model. We first have to choose a class of a model that we want to use. For instance, a regression, a classification tree, and there are a bunch of these models available for us. Second, we need to choose some hyperparameters. Those are basically parameters that kind of determine the behavior of the model. They're called hyperparameter because each one of these models has its own parameters that are estimated from the data as we see. So you can think about hyperparameters are metaparameters that the designer decides before fitting the model to the data. Next, we need to arrange our data into the feature matrix and the target vector, as we've seen above. And then we can use a function called fit in order to fit the data. Fitting the model to the data will estimate the parameters of the model. Once we do that, we can apply the model to new data. If we have a supervised learning task, we can use a function called predict, which will predict the outcome for another feature matrix. For unsupervised learning, we can either transform the data or we can even use predict if we have a clustering task. What we're going to do now, we're going to apply this machine learning pipeline with a supervised learning task, which is linear regression. Linear regression, as the name implies, basically rests on estimating a linear relationship between the X, the feature matrix, the X variable, and the Y variable. The simplest case is when we have 2 variables. We have only one X and one Y. Because you can imagine these 2 variables as, the observations as points on a plane, and the linear regression kind of boils down to estimating a best line that goes through these data points. In this example here, I simulated data, an X and Y, and you can see here that the true relationship between Y and X is Y is equal to 2 times X minus 1 plus some random perturbations. And this randomness can be the result of some measurement error, the lack of our capacity to measure these things in exactly their same values, or probably because we're missing something here. Again, this is simulated data, and the idea here is that we want to uncover this true relationship from the data points that we have. What I have done here, I just plotted the data points. And you can see here that when we plot it, we can see there is a linear relationship between X and Y. So first, we're going to choose a class of a model, which is a linear regression in this case. The next step is to choose the model hyperparameters. In the case of a linear regression, there are multiple hyperparameters that we can choose. For instance, do we want our line to be to go through the point 0, 0, or do we want the line to have an intercept? That's one hyperparameter. In our case, we can force it to go through 0, 0, or we can allow it to have an intercept. Do we want the model to be normalized? Do we want to process features? We will see some of these options in the future. Those are the set of the hyperparameters that we have to choose prior to fitting the model to the data here. In our case, we just created a simple linear regression and we set fit intercept to be true because I want the model to have an intercept. The next step is to basically arrange the data into the feature matrix and the target vector. Now my data here is called X, and if you remember, X used to be one vector of points here. It's an array. So it has one dimension. If you do x.shape, it's going to tell you that it's 50 observations. Scikit-learn insists on this data being a matrix. So even if you have one variable, you still have to put it in a matrix format. If your data is an array, such as this one, you need just to reshape it so that it shows as a matrix. And this is what I have done here. Now, you will not worry about this step if your data in a data frame, because if you use fancy indexing, you will get a matrix anyhow. This step is only needed if you're using a list or an array to create your data. So we're only going to worry about it for this example here. Once again, the point here is that even if you have one variable, it has to be in a matrix. Like this one, it's an array and the shape is 51. So 50 observations, one variable. Next, we're going to fit the model to the data, and this is done by calling the function fit and passing x and y here. This will basically estimate the model parameters, right? Don't confuse these with the model hyperparameters. The model hyperparameters are pre-specified. The model parameters will be fit by using the data. So this step will not take long in our case. Let's make sure we have the data loaded here. So I'm going just to repeat these steps again. Okay, and in the case of a linear regression, we have two set of parameters that it estimates. The first one is called the coefficients. And you can think about this coefficients as the slope of the line going through the space here. And that basically should be very similar to this number, because that's the number, the coefficient that we want to uncover using the linear regression algorithm here. We basically want to fit a line through these points so that the relationship between x and y is the coefficient itself. The intercept is where this line goes through the x-axis. In this case, it's the y-axis. In this case, it should be -1, right? Because when x is 0, y is -1, and that's called the intercept. So once we fitted the data here, we can inquire about our coefficient and our intercept. And you can see here that the coefficient is 1.9776, very close to 2, and the intercept is -0.90. So it's not -1, but it's close. Next, what we're going to do now, we're going to predict labels for unknown data. So what I am going to do here, I'm going to create a bunch of values from -1 to 11. And then I'm going to create another feature matrix called xfit, and I'm going to predict the feature matrix here. And I'm going to plot these points as well as the line. And you can see here that the line itself is fitting these points. So that was a hypothetical example using simulated data. Let's run a linear regression model using kind of a real data set. This data set, cars, is basically data about cars of multiple brands, of multiple countries of origin, and some information about the cars, including, more interestingly, the miles per gallon, which we probably want to explain here. We want to predict fuel efficiency based on all of the features, other features of the car. In this data set, we have multiple features, right? So we have the acceleration, cylinder, displacement, horsepower, no name if you want to use name, which probably not very meaningful, country of origin, and the weight of the car. And what we can do, we can start doing some visualizations just to understand how some of these features relate to the target array, the target variable, which is miles per gallon. So for instance, if I relate these two variables using a point graphical mark, kind of like a scatter plot, you can see that the higher the weight is, the kind of lesser miles per gallon is. So we intuitively understand this relationship, and this is not surprising. I'm going to do two linear regression models. First, I'm going to do one variable, so feature matrix containing one variable, and then we're going to add more variables to the feature matrix. So I'm going to extract X from data using fancy indexing. Again, it's important to use fancy indexing here because we want X to be a matrix rather than being a vector. So that's, even if we have one variable, it's very important to use fancy indexing. And my Y is the target variable, which is miles per gallon. Next, I'm going to create a linear regression model. I want to fit the intercept, and I'm going to call the function fit to fit the model to the data. Next, I'm going to take a look at the model coefficients here. So you can see that the coefficient is minus 0.0076. So each 1 pound increase in weight is associated with minus 0.0076 change, which basically 0.0076 decrease in fuel efficiency. That's basically the coefficient, the slope of this line. And the intercept is 46.21. And that intercept means that, absent any information about my X, which is the weight of the car. So if the weight of the car is 0, which doesn't make sense, and in this case, the fuel efficiency will be 46.216. Of course, this doesn't make a lot of sense because we don't have a 0 pound car, but that shows you where this line, hypothetical line, is going through the points, we're going to hit the y-axis when x is 0. So what I'm going to do now, I'm going to use the model to predict the same feature matrix. I'm going to predict the input itself, x, and I'm going to get y fit. And I'm going to store this in the data as another column called data predicted MPG. So right now, if we take a look at our data, we have two MPG variables. There is the true miles per gallon, that's the observed, and we have the predicted MPG, which is the predicted MPG using our linear regression model. Now again, you can take a look here and you can see that, they're kind of similar, but there is some discrepancy. There are two ways to look at this discrepancy. One way visually, to plot it, to see how well the model fits the data, and the other one is using some goodness of fit measurements. Let's start visually inspecting the model. I'm going to create two charts. One chart is going to be encoding the original data, weight in pounds and miles per gallon, using mark point. The second one is going to use a line mark, graphical mark, and it's going to encode the same x, weight in pounds, but the y is going to be the predicted miles per gallon. And that's going to be our regression line, and I'm plotting those two lines on top of each other. So if you take a look here, you can see that we fitted a line through this data, and that's the concept of a linear regression here. Of course, the data is not completely on the line, there is some spread. And this spread is due to many factors, including some measurement errors, but also because there are so many variables and we only looked at pounds here, the weight in pounds. So that discrepancy in between the actual observed value and the fitted value is called a residual. What I'm going to do here, I'm going to plot the residual. I'm going to create a line that goes through from the true miles per gallon to the predicted miles per gallon. So those vertical lines are called the residuals. Those are the errors that my model is committing when we're trying to predict the data. Okay, so overall the model goes through the data, but there is some errors that it kind of commits because it can't predict all of these points accurately. One way to quantify these residuals is to take the difference in between the true y, which is the observed miles per gallon, and the y-fit, which is the predicted one. Now, you can think that we want to aggregate these values somehow. We cannot take the sum because some of them will be positive and some of them will be negative, so it will be deceiving just to sum these values or take the average. So one way to deal with this problem is to take the square of these residuals and take its average. Thus, average of these squares is called the mean squared error. The higher the mean squared error, the less accurate the model is. So one can take a look at the mean squared of error and judge the performance of the model. The problem with the mean squared error is that it's not bounded. It goes from 0 to a very large number depending on the ranges of the values that we have. So we don't have an idea about how it scales. A scaled version of the mean squared error is called the R2 score. And the R2 score ranges from 0 to 1. 1 means the model perfectly predicts all of the data, and 0 means it doesn't do a good job at all. So if we evaluate the R score of our linear regression model, it's almost at 70%. It means this model captures 70% of the variance in this data set. So that's an okay performance, but it's not terribly good. Depending on the application, we may want to strive for a higher R-score value. So what I'm going to do now, I'm going to introduce more variables to the regression model. Now, the beauty of doing a linear regression only when we have one x is that we can visualize it. The moment we have more than a variable, it's become harder to visualize simply because we can only visualize 2 variables, right, on a space. 3 variables if we do a 3D visualization, which is not very useful. More than that, we cannot do it because we don't perceive more than 3 dimensions. So it becomes more difficult to visualize, but there are some workarounds that we can employ, such as visualizing the relationship between each feature variable and the outcome variable. In this example, I'm going to take here, and I'm going to convert it to an integer. Again, it has to be a number. And most likely, I have already converted it to an integer, so hence I don't need to do the conversion another time. Right, so here is now an integer. And what I am going to do now, I'm going to plot the relationship between weight in pounds and miles per gallon. This is what we have done above. But also the relationship between year and miles per gallon. So you can see that over time, generally speaking, cars have become more fuel efficient, right? The miles per gallon is increasing, although you have like a large variance, right? There is so much kind of spread in these points. So it seems that here should add some value if we add it as a feature to the model. And this is what I am going to do now. I'm going to construct my feature matrix to be weight in pound and year. My target variable should be still the same. Next, I'm going to fit the model here and take a look at the intercept and the coefficient. The intercept is basically where the line intercepts when both weight in pounds and year are 0. So that obviously doesn't make sense here because year is bound from 1970 to 2014. However, the coefficients are a bit useful here. Now we know that each increase in pound is associated with a decrease of 0.0066 in miles per gallon, but each 1 year increase is associated with an improvement of 0.73. miles per gallon, which is kind of the relationship we've seen with this scatter plot here. What I'm going to do now, I'm going to do the same. I'm going to fit my feature metrics to get the predicted MPG. So right now, if I take a look at my data frame, I should see three MPG variables: the observed variable, the one that we predicted from the first linear regression model, and the one that we predicted from the second one. What I'm going to do now, I'm going to evaluate my mean squared error, and you can see that it's lower than the previous value. The previous value hovered over 18. And I'm going to evaluate my R score, my R2 score, R squared, which is now 80%. So this is much better than the previous one, which was 70%. It means our model does a better job fitting the data. We gain 10% of, fitting accuracy, so to speak, by just adding the variable year. Now I'm going to do the same here. I'm going to plot I'm going to plot just a relationship between one variable and the other one, and you can see here that the line zigzags in between the points, and the line zigzags simply because there are two variables, and this is only plotting one of them. And actually, we did not fit a line. We fit basically a space, a two-dimensional space, because we have now two variables. So one can still visualizing using three-dimensional visualization. Unfortunately, Altair doesn't have 3D visualization capabilities. But the idea here is that there is a hidden dimension that you don't observe. That's the same case in here. If you visualize the line, it doesn't show like a line, it's zigzagging, and it's zigzagging because it's depending on the other dimension that we don't see, which is weight in pound. And that's the basic idea, and we can keep improving on the model. For instance, we can incorporate the origin of the car in our model. This is an interesting variable because we know intuitively from having some experience with cars that the country of origin matters, and some countries manufacture more fuel-efficient cars than other countries. The origin here is a string variable, so we need to convert it to a variable which is not string. I'm going to use the function getDummies on my data frame. The basic idea here is that I want to convert that string variable to a bunch of numerical variables. And those variables are called dummies because they encode that string variable because that string variable has three values, either Europe, Japan, or USA. You've got three variables here: Europe, Japan, and USA. If the car is from the USA, we've got one on USA 00 in Europe and Japan, and vice versa. So those three dummy variables will be encoding the categorical variable, which is the country of origin. So what I'm going to do here is exactly the same. I'm getting my X and my Y, except that my X now has these three dummy variables to encode the country of origin, and my Y variable is the same. So I'm going to create my model and just fast forward, just do the R score, the R square score, which is now 0.81%. So one can see here that it's a bit better than the one that only incorporated weight in pounds and year, although it's not much better than it. If you take a look at the coefficients here, you can see that the coefficient of origin Europe is 0.59, origin Japan is 0.79, and origin USA minus 1.38. That basically tells you that Japan manufactures the most fuel efficient cars, followed by Europe, followed by the USA. This process of kind of trying to figure out what features in our data to use and whatnot is called feature selection. This is a topic that we will revisit in the next lectures.